Classical Physics Tutoring, Chapter 5, Section 7, EM wave. Okay, electromagnetic wave is so-called EM radiation. A lot of people don't know what the EM wave is. EM wave is electric field changing by time and propagating in space. Okay, that's include the light, microwave, and TV signal. Those are all EM wave. Okay, so it's said wave, but actually it has a particle characteristic. So we get into the quantum mechanics world in this subject. But here we look at the wave side of the EM radiation. Okay, it's a direct derivation from the Maxwell's equation. You remember we have this equation, right? This is a Ampere's law, and if you take a derivative by time again, we get this. Now, do you remember in the previous video I explained E cause B and B cause E again, and has a negative feedback loop. Okay, so the here change of the B is going to cause curl E. So we plug in there, right, because this just constant. Then we get the double curl E equals double derivatives of time, and this one in the vector calculus we expand it and it's become simple second degree derivative. So we get this, and this is the wave function in the 3D, and the constant c happen to be light speed. And you look at this equation, light speed, it doesn't matter where the light is emitted. Okay, this is a problem bothering Maxwell and everybody else at that time. Say you are on a spaceship already half c speed, very fast, and you issue the light speed according to this equation. It's still this speed, light speed. It's not like 1 plus 1.5 c. Okay, so this is where the special relativity theory comes in, and we're going to learn that in the following videos. But the equation suggests that light speed is light speed all the time. It doesn't matter where you issue the light speed. Okay, so this is the kind of area that Maxwell was puzzled and everybody puzzles, and it's lead to the Einstein's idea of maybe light speed is constant all the time. Okay, so the actually equation was derived after the existence of EM wave. What happened is they tested, they suspect some kind of energy coming out, so they put some wire and alternate current, and they took some wire with a distance and measured, and here you go, they detected, that means energy, some kind of energy flies in the space and reach here. Okay, and this kind of experiment has been done before this equation derivatives. So after this experiment, they figure out this negative feedback should create some kind of wave, and here you go, they came up with the equation. And coordinate equation, the polar coordinate, when it's emitted from the single point to the 3D space, we can get the equation like this. The solution, it's going to be sine wave, of course, right? I mean, so far in physics, everything is sine wave, and you haven't seen anything else, but the reality is much more complicated than just sine wave. So the way it's propagated seems to be that electric field and magnetic field alternate, right? And they are orthogonal. When electric field goes up, orthogonally magnetic fields goes up and go negative side, and that's the way direction of wave goes. And with the time is the, if you see this wave, it look like this, and when time pass and more time pass, then it's go back and go up, it's repeat. Okay, so time is not shown in this wave propagation, but that's what it is. This is one way to express the EM wave. And classical physics, that's what it is. And if you go to the quantum mechanics, things change. For example, each wave has a distinct energy, which is E equals hc lambda. This lambda is wavelength, c is light speed, and the energy is Planck constant, is given by this. And this energy, you have to know the exact meaning, is the energy for each wave. And what do you mean each wave? Wave is continuous. Well, quantum world, this wave is you are emitting particle continuously, and that's why you see the wave, but each single wave has this much energy. Okay, so in electron volt, high energy particle, it's going to be over lambda micrometer. Okay, so each wave has energy, and this is important because it's not like a classical sense wave. The wave carry energy, and a single energy carried by a single wave. But the EM wave, each particle carry this energy. That means when wave hit something, it has a molecule inside, right? And atoms. It's hit atoms. Only single particle hit, not the entire wave energy. If entire energy hit single atom inside, this is gonna be gone, right? But only this much. And this energy is, unless lambda is very small, means high frequency, high power energy, it's when it's hit, it's bounced like that, leave some energy in the particle, the atoms of molecule, and this is usually much less than bonding energy. Bonding is this energy. So what happened is it won't change the molecule structure, but instead it just increase the vibration. No atoms. That means temperature goes up. Okay, and that's all it is. It doesn't change the molecule structure. Temperature goes up. But if temperature goes up high enough, then this bond break, right? That's you're cooking meat in the microwave oven. Its temperature goes up, then temperature is going to change the food. Okay. This EM radiation microwave doesn't change the food. It need to give energy continuously to each atom, and temperature goes up. This vibration is temperature, and temperature break down the molecules, so you're cooking food. Okay, you're cooking food by temperature. So if it's silly that if microwave hit your body and cause something, it won't cause anything. It may heat up a little bit. So the infrared heater, it's come from infrared heater, is going to warm up your skin. Okay, that's all it is. But if you warm up too much, it's become like a barbecue pork, right? The skin get burned and cooked. Okay, so it's two different things: the energy carried by each wave particle and total energy given by EM radiation. Total energy given by EM radiation is going to change temperature and burn the things. Okay, each particles, if it's a X-ray or gamma ray, lambda is very short. That means energy is very high. So single hit may, like a pool ball on the pool table, the atoms away and cause the different molecule structure. And that's why ultraviolet signal may cause skin cancer, because it may change the DNA molecule. But below ultraviolet light, energy level each molecule carry is too low to change anything. Okay, so when you have an antenna like that, the single tower, and you give voltage, alternate voltage here, right? So the E change this way, then magnetic field change orthogonally this way, just like this diagram. So the wave emitted is going to be cosine basically, but it's attenuate by the distance r. Okay, and that means when you send a signal to the moon, distance is 300,000 kilometers. It comes in here. The signal becomes so weak, it's not easy to detect. The same thing, signal from the moon need to have a pretty high power to send a signal to the Earth. Otherwise, it won't. It's become the noise levels, and you cannot communicate. Okay. Some video talking about communicating with probe at the edge of solar system. That's probably impossible because distance is too large, and you can never get the signal from that kind of probe. And probe has only a little battery with a solar cell, whatever. This is just imagination. Okay. So electromagnetic wave, basically, in classical sense, it's a wave, and speed is 300,000 kilometers. And practically, the microwave we use is like a 3G communication. Microwave is 2.5 gigahertz, and this is much longer lambda than water molecules. Why this excites water molecule? Water molecule actually has a chemical bond and creating large lattice structure. Lattice. And this large lattice structures resonance is about 2.45 gigahertz. And that's why microwave is set to this frequency. Then this lattice is going to vibrate. Then water temperature goes up. and you can cook the food. Okay, Wi-Fi, 4G, 5G is around this frequency range. Okay, and it's penetrate the human body somewhat, but because there's not much interaction with molecule, and when it hit the molecules atom, its energy level is not large enough to break the bond. So DNA typically is safe at this frequency. Okay, the backbone 30 gigahertz. The rain in the air is going to absorb somewhere between 20 to 30 gigahertz, and you can't use this frequency because when it's rain, it's all absorbed and you cannot do the communication. So from here it's jumped to 30 gigahertz, and even higher is 90 gigahertz, and some military use it, but I think in futures commercial world also use it. And 1 terahertz upper limit of microwave, and some military is making a radar system using this extremely high frequency. Beyond that, it's going to be visible light, and you're getting plenty of EM radiation from sun every day. Okay, and the sun's radiation include infrared 400 terahertz all the way to 700 nanometers, 770 terahertz visible lights. Okay, and among these visible lights, ultraviolet is high energy. Each particle has, remember, lambda is very low. So the energy level become very high, and this particle, ultraviolet high energy particle, hit molecule, and molecule sometimes change, and plants need this energy to create the new molecule. That's called photosynthesis. Okay, photosynthesis need energy from the high energy EM radiation. So plant get plenty of EM radiation and grow healthy because they utilize all the energy, say 80%, but this energy is high energy, harmful, maybe 0.00001% of the time it's cause a problem. Okay, but its benefit overwhelm the harm, and that's what it is. Plants want high energy, ultraviolet, but it has a both side. Beyond that, it's become X-ray and the gamma ray. They are very high energy level, and it's gonna change, break the molecule bonding. So DNA is exposed at the danger, and doctor recommend to avoid these exposed for a long time. Okay, so I hope you enjoyed this video. If you like, please subscribe.